Today, I'd like to talk about LatentLLM, a new technology to compress large language models in a zero-shot manner. I am Toshiaki Koike-Akino from Mitsubishi Electric Research Laboratories, MERL, in USA. We first address our motivation towards green AI, then we show our model compression method, LatentLLM, which gives three interesting insights on preconditional, junction, and tensor decomposition. After some benchmark experiments to show its benefit, we will summarize our talk. According to some articles, the required training compute has increased exponentially, nearly tenfold every year. Also, AI models are getting bigger over the past decade in nearly exponential manner. Then, training such large models requires high energy producing multi-fold carbon emission of a single car lifetime. More recently, AI data centers are driving up electricity demand and prices over the world. So how to realize greener AI technologies is getting more important to solve this social challenge. For example, green AI technologies include data efficiency, training efficiency such as PEFT, and model efficiency such as quantization, pruning, and decomposition. In this talk, we focus on the decomposition. Our LatentLLM gives a solution to globally decompose multiple modules into latent modules such as Multi-Head Latent Attention. Latent attention was introduced in DeepSeek v3 model to improve efficiency. By using low-dimensional projection for QKV, query key values, it has a significant reduction in computation and KV cache. But how can we convert your LLMs into such DeepSeek-like models? Our method provides an efficient solution by exploring preconditional, junction, and joint decomposition. Let me first discuss the preconditional. Compressing pre-trained LLMs without fine-tuning can be done with plain singular value decomposition (SPD), which locally minimizes the approximation error between original weight matrix double and decomposed low-rank matrix B by A. This can be significantly improved by ASPD considering the activation X to minimize the approximation error of double by X. Instead of using the calibration data X as is, ASPD introduced a preconditional matrix P to capture its statistics. After a simple calculation, we can show that the root covariance is optimal as a preconditional. However, the original ASPD uses L1 norm as a preconditional, and many such suboptimal preconditionals are used in different contexts, such as pruning and quantization. For example, GPTQ uses Hessian and AWQ uses L1 norm for quantization. Wanda uses L2 norm for pruning, and Corda uses covariance for LoRa initialization. Our LatentLLM uses the optimal root covariance. Next, we move on to an interesting insight we found on the junction matrix. Now ASVD with proper preconditional can decompose into low-rank factors U, S, V, left singular, singular values, and right singular. However, we need to map them onto our low-rank projectors B and A. This mapping has no unique solutions. In fact, injecting any full-rank matrix J and its inverse has no impact. Using this junction J, we can write a general solution to map USB into BA. Because J has no impact in performance, most papers do not care the choice and simply using identity or symmetry singular junction. Interestingly, we found that some choices of junction matrix can be significantly beneficial to reduce the complexity and memory. For example, a particular junction can convert A or B into block identity matrix. Here, I want to show why such a junction matrix is useful. This figure plots the number of parameters when decomposing the original weight matrix of size D by D. When using rank R decomposition without junction matrix, the number of parameters will be 2RD. As you see, the number of parameters is not always smaller than the original size. it can be twice large at the worst case. Now, when we use a proper junction matrix, the number of parameters can be always reduced from the original size across any rank. This is significantly useful to realize compact LLMs, having lower complexity and memory. Next, we describe our attention-aware joint rank reduction method. Most typical LLMs have attention module and MLP module. By using ASVD for Q projection, K projection, and V projection, we can convert multi-head attention to latent attention. To further compress the LLMs, we can also decompose output projection, up projection, and down projection. However, such individual tensor compression is only good to minimize local approximation error. We instead decompose multiple weights jointly to minimize more global errors. In particular, we derive a mathematical solution to jointly optimize a pair of QK, VO, and UD projections. For joint QK compression, we consider minimizing attention map error, which is based on query value dot product. After some mathematical reformulations, we found an interesting fact that it is fundamentally high-order SVD problem. The QK dot product can be written by Einstein sum, and we verified that the tensor G can be optimally approximated by 3-order Taka decomposition. Also interestingly, joint VO compression can be formulated in the same way. For joint UD compression in MLP module, we use decoupled loss minimization trick, similar to sparse LLM. The global loss function in MLP includes nonlinearity, and thus it is difficult to solve the optimal low-rank decomposition jointly. We reformulate the loss into linearly decoupled loss by introducing intermediate variable z and z prime. Doing so, we can derive closed-form solution for z given z prime and vice versa. After only a few rounds of alternating optimizations, we can obtain good solutions. This trick was originally introduced in sparse LLM for joint pruning, but we realized that the same trick can be also applied to tensor decomposition. The first experiment we show here is how much latent LLM can reduce the complexity, inference time, and memory for OPT 7 billion model. By decreasing the total number of parameters through compression, we can linearly decrease flops and max as expected. The inference throughput can also increase, for example, twice speed up by 70% compression on A40 GPU. More importantly, the KB cache is significantly reduced by compression. For example, 70% memory reduction is achieved at 50% compression. Next experiment is LLM benchmark on Wikitext 2. For both OPT small and large models, we verified that latent LLM can achieve the best perplexity score among state-of-the-art methods at any compression ratios. For both OPT and QM models of 7 billion scale, the same trend was observed. We then demonstrate the benefit of latent LLM for VLM benchmarks. Here we compress Lava 7 billion model for science QA visual reasoning tasks. Again, our method achieves the best performance. Also, our method keeps the highest accuracy across different grades, modality, and subjects of QA tasks. Another VLM benchmark on text PQA, we evaluated QMVL 7 billion and 3 billion models, as well as Lava 7 billion model. For all VLMs, our method performs the best. Notably, ASVD without using root covariance had nearly 0% accuracy, and thus it shows the importance of the preconditioner. Now, let's conclude my talk. We discussed the optimal preconditioner, the junction matrix, and joint tensor decomposition. Our method can convert any LLMs into DeepSeek-like compact LLMs without retraining. We showed significant KB cache reduction and speed up. Then we demonstrated the benefit in LLM and VLM benchmarks. We plan to apply to HAI. Please contact me for any comments. Thank you.